All right, let's go over exercise 13.1, which is one of my favorite exercises in the whole textbook, so it's gonna be fun, at least for me, I promise. This is an inventory, an optimal inventory problem, and as such, we can know in advance that the solution takes the form of an SS solution, where small s stands for the critical level at which the firm is supposed to place an order to replenish its inventories, and capital S stands for the optimum order size. Given the fact that we have a random shock variable that takes two values, 0 and 1, and it is the variable that describes the demand for the inventory. We know that the critical level where the firm is supposed to place its order is 0, because any other solution would make no sense. For instance, if S was 1, then the firm could meet demand next period, because maximum demand is 1. So, for instance, if S was 1, it would make no sense, because maximum demand this period is 1, and in this case, given the features, the basic characteristics of the random process, the firm could meet the demand with no problem at this level, so it would make no sense, and S 0 is the only reasonable policy for the firm in terms of the critical level where it's supposed to place its order. Okay, so what we are looking for is the optimum order size. All right, so let's try to expand the problem. With a non-zero probability, there is positive demand, in which case we have an income, and this is the price of the product we are selling, and this is the case where demand is 1, so inventory goes down by 1 unit before next period. And there is another non-zero probability that there is no demand at all, so we take the same inventory to the next period. In a few steps, we can reach, with very simple mathematics, we can reach this form. Yep. By realizing that the same function shows up on both sides. So we can express Vx in terms of Vx minus 1. All right. Let's bring in a new parameter. So using, first of all, we want to ensure that this parameter falls between 0 and 1 strictly. So we want to we need to choose beta and theta appropriately to ensure that this inequality holds. And by using this notation, we can realize a recursive pattern in the equation, in the value function. So we can go down step by step until here we reach 0. The number of the steps through which we reach 0 depends on the size of x. So it's not correct, it's not fully correct, but hopefully it's gonna be instructive. So let me expand. Let me build these equations into a single equation full of brackets, I know, but hopefully you will realize the pattern, another pattern. So it's not too nice, but if x is 4, I picked 4 for x completely arbitrarily. This equation reads, this is b. This equation reads as this line. This is beta, sorry. And it's easy to realize that this letter equation consists of 2 parts, because here we have the value function. So in another step, we can squeeze the first part into a bracket. And it's gonna be very useful. Okay, this is a finite geometric series. This is a finite series, the length of which depends only on the size, on x, which was 4 in this case. So no surprise, we reached 0 in 4 steps. So let's try to find the pattern in general. So the value function can be written this way. Yes, this is still a finite geometric series, so we can squeeze it further. And this is the guy that stands for the series in the previous line. All right. And in a few steps, we can have this equation, this form. Okay, so we have two value functions, the same value function at x and 0, and for simplicity, let's introduce another parameter and by using this new notation, okay, it applies to, it's true of any x. So it is also true for y. It's also true of y, where y is the order size. And this equation is most important because in this value function, this is the unknown value function, v0. And v0, we can expand, we know something about v0 because this is the level, 0 is the level where the firm is supposed to place its order with some costs. These are the costs. And please remember that y is an integer, so the optimum order size can be 1, 2, 3, 4, 5, 6 or something, an integer. Okay, so by going along, we can expand this latter equation This is going to be exciting because so what we have done is building this equation into the value function at 0. So, ta-da! We have a very fancy value function which I want to highlight because this is the equation which we are going to use for finding the first order condition. But before finding the first order condition, we want to ensure that the value function is strictly increasing in x. So what to do to make it sure that the value function is strictly increasing? Given that the value function is this guy, no surprise, we have the following function that describes its monotonicity. All right. Given that b1 falls between 0 and 1, it's sure that this part is strictly negative. For positive integers, this part is positive, and it is supposed to be strictly positive, and to this end it is supposed to be negative. So later in the discussion we will see that this assumption, so we need to assume that this inequality holds, and later in the discussion we will say that we have a reason to assume that this inequality holds. Okay, so let's turn to the first order condition. I have just highlighted that we are working on integers, so we will have no first order condition in the usual sense. So instead of differentiating, we are going to work with differences. So we are going to try to find the optimum order size by calculating differences to understand how the order size affects the value. So our question is the following: what is the use? What is the what is the use? What is the consequence when we increase the order size by one unit? So let's do the math. Let's try to do the math. So as I have just mentioned, we increased the order size by 1 unit, and we want to calculate its consequence, the difference. And this is the case where the order size is smaller by 1. Okay, so we are working, just to be precise, we are working with this equation. So we are using this equation to shed some light on the consequences of an increase in the optimum order size. Please be careful with the signs. Okay, let me give you the full calculation, because we can simplify the expression, the equation, in each step. in the previous step, we could get rid of some parts. So it's going to be shorter. It's going to be shorter, I promise. And in the next step, we can get rid of these parts. So we have this equation. Okay. And we realize that this part and this part, they are the same. So finally, we have this expression. Yep. And this is an important step. I'm just checking. Yes, it's correct. So this is an important expression, so let me highlight it. Because this is the equation which we are going to use as a kind of first order condition. Given that these inequalities hold, it is also true that, it's easier to highlight here. So this guy is strictly positive, and given that we assumed previously that this expression is negative, where here I think I mentioned that we were going to use this inequality soon, and the time has come. So given this inequality, this guy is strictly positive. So everything is positive in this expression. But this is the only term that depends on y, on the order size. And this part of the expression is strictly decreasing. So in in a continuous case, we should find the optimum order size y by ensuring that this equation is zero. But given the fact that we are working on integers, we cannot be certain that finding the optimum order size will make this equation zero. So we need a trick. So we are going to find the optimum order size by knowing that over the optimum order size, this equation is going to be negative. So once again, we are going to maximize the v0 value function by using this equation. Let me highlight this equation. And this maximum is where the first order condition is zero. But we are working with integers, so in this case, the most we can do is to get as close to zero as possible. So this is the reason why we need to do some tricks. Let S stand for the optimum order size, and we know, as I have just mentioned, we know that the optimum order size, any higher order size would make the first order condition negative. So we are going to use this fact. This is a first order condition. So we know, and this is the point we were struggling for. So S is the optimum order size, but over S, the first order condition would be negative. This inequality can be solved for S, even if this value function is unknown for now, but it can be solved. Optimum S depends on the value function, while value function depends on the optimum order size. So the value function is the function of itself. So we can only describe it in an implicit form. If we have S, then on the basis of our first order condition, we can use the optimum order size in the Bellman equation, because it is still true that the optimum policy solves the Bellman equation. This is the Bellman equation which we solved by finding the optimum S, which is unknown, factually unknown for now, but we know we can find it, so it exists. Okay, so the optimum order size solves the Bellman equation. So it is great because the optimum order size helps us to find the value function v0, and this is great because v0 is a part of the general value function vx. So with some manipulations, we can go further. This is the optimum order size. Okay, and it follows that this equality is true, and from this, please remember that we have only the value function at 0. So what we have, so we can solve this equation to this form. We can arrange this equation into this form. Which is positive because this guy is strictly less than 1, and this result justifies our previous assumption that this difference can be supposed to be strictly positive. And this is exciting. This is most exciting because this expression can be put into the first order condition, which now looks like this. This is important because now we have a first order condition in which we don't need to struggle with the unknown value function. So we need to find an integer s beyond which this inequality holds. So this is a step-by-step iteration. We can start out with s1, 2, 3, 4, 5. So we are working with integers, and we find an s beyond which, I mean for the next integer, this inequality holds. So we have a unique s that solves this inequality. So we have the optimum policy, and s is also found. So we are done at this part of the problem. Part B of the problem is not too long. We have the optimal SS policy, and we know that the critical level of the inventory is 0, and S, the optimum order size, depends on the parameters of the problem. So everything is clear. That small s is 0, it means that we place an order only at the 0 level of the inventory. So until we reach this critical level, we just keep selling and waiting for the inventory to reach the 0 level. It is important to realize that the state space X is not bounded. There is no upper bound because S, the optimum order size, cannot be an upper bound. It is an upper bound only if the starting inventory is not greater than the optimum order size. If this condition holds, then we start from somewhere below the optimum order size, then we reach 0 sooner or later, and we jump back to capital S. Okay, we need to describe the transition function P. It is not too difficult. The chance from going the chance of going from I to I minus 1 is theta if I is greater than or equal to 1. Pii is 1 minus theta if I is greater than or equal to 1, and we have 3 further lines, and and 0 otherwise. It is important to realize how timing is important in this exercise. At the beginning of each period, the firm places its order immediately, and the order comes in right before demand may come up. So when inventory is 0, so this is the critical inventory level, before demand comes in, the firm can fill up its inventory to the optimum level. So if there is positive demand, then from initial 0, I am talking about this case, from initial 0 we can go to S minus 1 with probability theta, and from 0 we can go to S with probability 1 minus theta if there is no demand. So if there is demand in the period at the beginning of which we had 0 inventory, then the stock is going to be S minus 1. If there is no demand, then from 0 we go to S by the end of the period. The ergodic set is the inventory levels below S, because this is the state space with that we cannot leave. So if we have an initial stock which is higher than S, all the inventory levels above S, these inventory levels belong to the transient set. It is also important to realize that the ergodic set contains one huge cycle, which is not a problem, because cyclicality is a problem only if we have multiple cyclical subsets in the single ergodic set. So this was part B of the problem, and we are going to part C. In part C of the problem, we are looking for the unique invariant distribution. First of all, we want to show the existence and the uniqueness of this invariant probability distribution. From the fact, it is really important, from the fact that there is only one ergodic set without multiple cyclical moving subsets, it immediately follows that there is a unique invariant measure, and that the rows of the limit matrix of P, these rows are the same. We have two theorems to refer to. One is theorem 11.4 and the other is theorem 11.12. both theorems would do if we want to show that there is a unique invariant probability distribution. Here, let's use theorem 11.12. This theorem refers to condition M. So if condition M is satisfied, then according to theorem 11.12, there is a unique invariant probability measure. So there is one thing to do. We need to show that condition M is met in this problem. Just a kind reminder, condition M is a condition according to which we can get to any subset A of the state space from any initial state in finite steps. It's very easy to show that the condition M is met in this exercise, because please remember, we have only one cycle in the ergodic set. So from any initial inventory, there is a non-zero, strictly positive probability that we reach the zero level of the inventory, from which the firm places the order and the inventory jumps to S or S minus 1, depending on the next demand shock. And there is also a strictly positive non-zero probability that we reach the zero level in finite steps. So formally, this probability that from any S to any A, the probability of getting from any S to any A is strictly positive if the state after n steps is in A, and if not, then the other side, on the other side, this probability is strictly positive. So condition M is met. Condition M is met. So there is a unique invariant probability measure to which the rows of the powers of the Markov matrix, the stochastic matrix, are converging. Okay, this process is a first order Markov chain, so we can describe the whole process with a Markov matrix. So let me give an example in which S is chosen arbitrarily. This is just an initial demonstration, and right after this initial demonstration we will see the general case with some math. So what I'm doing now is describing the dynamics of the inventory on the basis of the optimum policy. So if you have a look at this matrix, then you can realize that from level 0 there are two possibilities by which we can get to S or S minus 1 respectively. So this Markov matrix precisely describes the whole inventory problem of the firm. So this is a Markov matrix which is which has the dimensions of s plus 1, s plus 1. Okay, so as a first demonstration, let's work with this concrete example, and in the next step we will generalize our results. If we have a unique invariant distribution, so let's label this unique invariant distribution as P upper bar. To this unique invariant distribution, it applies that this is true. Okay, so for simplicity, let's reduce the dimensions. So let S be 3. In this case, I am simplifying because what is true in this case, it can be demonstrated that this is true to higher dimensions too. So we have the following Markov matrix. This is the same Markov matrix as we had previously, but in terms of dimensions, it's simpler. So I promise it's gonna be simpler to work with this matrix. So I am writing the same Markov matrix with lower dimensions, and given that this is true of the unique invariant distribution, we can write the following. I am writing this unique invariant distribution. You know, it's a 4-element vector. The sum of the elements of which is 1, and we are supposed to get back the same probability vector. It takes some math, so you need to calculate this multiplication, and in the end, after a few steps, we will have 4 equations. This is the first one, this is the second one, this is the third one. All you need to do is to complete this multiplication, to do the math, and you will receive these 4 equations on the basis of this equality. So after doing the math, we have these 4 equations. What is important that theta comes up in 2 equations of the 4, so we can try to cancel, to eliminate this parameter. I think it's correct. Minus yes and yes. So I think both are correct. And from this, from the first equation, it comes from which we can write the following. Okay, and from this from these two equations, it follows. Two b equals 1 minus c, which because of the second equation, so b is 1 over 3 and c is also 1 over 3. And because of 1, a is 1 over 3 times theta. This is a concrete example which we will check later after generalizing this solution. If theta is 3 over 4, then a is 1 over 4. How can we generalize these results? We have a hunch. In the general solution, this is what we expect. So please remember, it's okay that b and c both are 1 over 3, but please remember that in our example s was 3, s is 3, so it might be the case that these elements in the unique invariant distribution vector both are 1 over s. So the results are dependent on the dimensions of the Markov matrix. So let's try to generalize. It's gonna be a huge matrix because now we don't want to set any initial value for s. So in general, the Markov matrix of the problem is a matrix of whatever dimension. A Markov matrix of whatever dimension, I mean. It's gonna be nice. Hopefully. We don't need to fully describe the matrix. We need only the structure, the patterns in the matrix. So this is, this is a very general version of the Markov matrix underlying this problem. So the same thing applies to the unique invariant distribution vector. S was 2 in the first concrete example where S was 3. S was chosen arbitrarily. But please be aware that the matrix has s plus 1 times s plus 1 dimensions. So the unique invariant distribution vector also has s plus 1 dimensions. So after doing the math, some general... Okay, so this is going to be our unique invariant distribution vector okay. So after doing the same math as we did previously, we have some simple results which we can use. So what I am doing is writing the results from the vector matrix multiplication. I don't need to, and I don't want to fully write all the rows. I cannot, because we haven't set any concrete value for S, so these are the last two. Please pay attention to these parameters. So you can realize that the first row, column and the last two columns of the Markov matrix are special. The other columns are quite the same. They are very similar, but the first and the last two columns are special. So this is the reason why we need to pay attention to this equation and to these two equations, because they are special on the basis of what we have just seen, on the basis of the Markov matrix. So there are two things which we should realize. So from the second equation, it follows, from which it follows, and we can go on. So after the first special element in the distribution vector, in the invariant vector, probability distribution vector, from after the first special element, we can follow this pattern. Okay. For a while, but when we reach the last two elements in the vector, this pattern, this previous pattern, is broken, because this is what applies to the last element in the vector, which can be simplified and eventually we are going to have this equation that describes the last element in the invariant distribution vector. This describes, the following equation describes the first element in this invariant distribution vector, and there is only one element missing, the item before the last element in the distribution vector. Hopefully it's correct. I'm checking, I'm double checking. Yes, it seems to be correct. From which it's not too hard. After a few simple steps, it follows that it can be described as a sum. Okay, so we have one equation to each special elements in the unique invariant distribution vector. When we add up all the elements in this distribution vector, we are supposed to get 1 as a sum. So here, this pattern has special importance because altogether, if we have S that sets the dimensions of the Markov matrix, we have S minus 2 pieces of these elements. I mean this one. So we have S minus 2 pieces of Pi, to which we add, this is P1, this is P S plus 1, and this is again P1. I'm not repeating myself, I'm doing this on purpose because this is and please be aware that PS is the sum of these two elements. So this is PS altogether. We can simplify this expression, and after doing this simple maths, we are going to have this equation. And altogether we have S pieces of Pi, from which Pi is 1 over S for I 2 up to S minus 1. Okay. And the special cases are described by these three equations. So let's check if this general solution works. Let S be 3 as previously in the concrete example, and let theta be 3 over 4. Then P2 is 1 over 3, P1 is 1 over 4, P4 is 1 over 12 and P3 is 1 over 3, which is the same result as we had previously. So our general solution works. There will be an extra exercise attached to this lecture. So we are going to solve the same problem in MATLAB. We will learn how to define a Markov chain in MATLAB, and we will work out the complete solution to this problem in MATLAB. Okay, so see you then.